Okay, so maybe we can start. Hello everyone. So today we will have another paper to discuss. It's also about VIT. And this paper is also from Google Research, but I checked all the list. It seems the author is very different from the author we discussed, of the paper we discussed before in the previous class. So this paper is more like a follow-up paper. We focus on analyzing the robustness of the VIT model by VIT comparison with the resonate, and also provide many of the experimental analysis of the model performance. Subject to different kinds of perturbations, also corruptions and adversarial attacks. And the presenter today will be Norman, right? Norman Sheikh. And let's give the time to the presenter. Yeah, Norman, you can start when you are ready.
All right. So, good afternoon, everyone. My name is Numan, and today I'm presenting this paper, Understanding Robustness of Transformers for Image Classification. So, until now, we have seen CNNs in all of the models, in all of the state-of-the-art models that have been used until now for computer vision. So, since the advent of transformers have we're seeing their use in the computer vision as well. So in this paper, the authors have compared the best performing transformer model, the vision transformer, with the previous state of the art, that is the resonance. So in this paper, they put the vision transformer through numerous tests. They perturb the input, they perturb the model, and they just check how it performs with respect to the previous state of the art, that is the resonance. I don't know how. Okay, so these will be the contents of this presentation. So first of all, I'll review the working of the CNNs, what is its inductive bias for the computer vision tasks, for the computer vision classification tasks. Then I'll go over the architecture of the vision transformer. We'll see how it works and how is it related to the transformer model. And then we'll start reviewing the contents of this paper. Then we'll start input perturbation. We'll just perturb the input to the model and see how the model behaves, how the model reacts to the input perturbation. And then we'll perturb the model itself. That is, we'll prune some layers, we'll do some lesion studies, we'll see the correlation of the representation of each of the embeddings as they chug along all the layers in the model. So yeah, that's the contents of this presentation. So moving on, I think we all know what convolutional neural networks are. They're the backbone of the current day computer vision models, and there are some properties that make it very suitable for use in computer vision. Its properties such as the spatial locality awareness, where it just sees the pixels in vicinity of each other and it processes pixels in vicinity. These are some properties that make it very natural to computer vision applications. Other properties such as translation invariance. So for example, if I have a picture of a dog and a dog is here, and a dog is towards the left hand side of the image, and other picture where the dog is towards the right hand side of the picture, we expect it both the times to predict that there's a dog in the picture. So there's translation invariance. No matter where the subject is in the image, it should be able to successfully predict that there's a dog in the image. And the other thing that lends this convolution and that lends these convolutional neural networks very well to the task of computer vision is that they are end-to-end learners. We don't have to do some hand engineering in these models. So as I said, these properties make them very natural for computer vision applications. As I already said, yeah, there are some strong inductive biases for computer vision tasks due to these properties. Because, for example, if I want to predict an image of a dog, and I see some pixels in the vicinity, I won't be expected to match a pixel that are very far away from each other to do my processing for a classification task. Since these convolutional neural network filters process the pixels that are in the vicinity, we just presume that there is a strong inductive bias for the computer vision task. And moving on, this is something called as the field of the effective field of the convolutional neural network. So, for example, if I'm doing some cats versus dogs classification. So, for example, the first of the convolutional neural network, the first of the layers will be effective in just finding out the edges, and the layers towards the middle of the model will be successful in 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 classifying or in finding some other high level features. So there's kind of a hierarchical structure. The first layers find low level features, the middle of the layers find higher level features, and layers towards the end find the highest level of the features. For example, if I'm training a model to see a dog, so the layers will just be able to classify, will be able to find the edges. The other layers towards the middle of the model will be able to find some other high level features, such as they'll be able to find the eyes in a dog, four legs. And the layers towards the end of the model will be able to classify a bit a very high level feature, such as a complete dog. So there's a sort of a hierarchical structure in this. That's very helpful. The other thing that the other features that we see in the current day models that really augment the processing of these CNNs is some layers such as max pooling. So these max pooling layers just act as distillation layers. They just distill the information that has already been processed by the CNN filters. So they lend themselves very useful, and they're they're seen in almost each and every modern day convolutional neural network pipeline. The other thing that is very useful in today's model is this residual connections, or otherwise called the skip connections. They are very helpful in doing some things, such as they allow the easy gradient flow to the earlier layers. There may be some the gradient may vanish if we are using a very long model. So the earlier layers may not receive a lot of gradient, may not receive a lot of proper gradient. So with these residual connections, with these residual and skip connections, we are able to provide them with a proper gradient necessary for backpropagation and for learning. And they may also be they may also be helpful to prevent the explosion, to prevent the exploding gradient. So these are the resnets, and these are the skip connections that we see. They help in proper they help in, as I already said, this gradient thing. They don't they allow easy gradient flow to the earlier layers. So this was ResNet. See, skip connections. These are very necessary for today's models. So now comes the vision transformer. So basically, it's a derived form of a transformer. After much success in NLP, the natural language processing tasks, transformers have been tried in a lot of computer vision tasks. In fact, this particular model, the vision transformer, even beats the previous state of the art, the ResNet 50, in some of the computer vision benchmarks, such as the ImageNet. And the thing to be noted here is that there is no inductive bias in vision transformers like there was in computer vision, like there was in CNNs. So we do not presume a spatial locality. We do not presume that spatial locality is necessary, because attention caters to each and every pair in the input embedding. So there's no concept of spatial locality in this. So there are no inductive biases. The model has to figure out its own. So this is the high level architecture of this vision transformer. It looks much like a standard transformer. So we just use the transformer encoder in this. So I'll tell you how this works. I'll give you a brief overview of how this works, even though this was presented the day before yesterday. So first of all, as we give the model some images, these images are first broken down into non-overlapping patches. These patches may be of different dimensions depending on the model that we're currently working on. So there are 3 versions of VIT. One that has 32 by 32 pixel height and width, and the other which has 16 by 16, and the other one which has only 14 by 14. So these patches may be of differing widths and heights depending on the model we're training on. And there are 3 versions of VIT depending on the model size. So there's basic, there's large, and there's huge model. So these models are categorized by the number of tunable and trainable parameters they have. So first, the image is broken down into patches, as I already said, non-overlapping patches, mind you. So now when these images are broken down into the patches, they are flattened into 1D vectors. And these 1D vectors are then projected on some other space in some other dimension. So for example, if its dimension was dA cross 1, it is projected to some other space where its dimension is only dy. So this is the task of this linear projection layer. This thing projects these 1D vectors into some other space. So when these are projected to some other space, after that, we also prepend a sort of a embedding like we do in the BERT model. The BERT model also uses this CLS token. We use a similar kind of a token here in VIT also. We prepend this token here, and we also add position embeddings just to preserve that positional information in the image, because it's broken down into patches and the model should have some way of knowing what the original position of the patch was in the original image. So that's the input processing. After this, all those vectors are fed into the VIT model. This VIT model is just a transformer encoder, as we see towards the right hand side of the image. We just feed all those vectors into the model, and we just read out the final representation of this CLS token towards the end to classify our things. So for example, we just read the representation of the CLS token of the highest layer of the encoder and just feed into the MLP head, feed into the multi-layer perceptron layer, and the output of this layer is our softmax, is our layer that helps us predicting things, that helps us classify. So that was it. The thing to be noticed here is that this model uses the same CLS token, and the other thing that the authors of the vision transformer try to do is they just kept this model as similar to the transformer encoder as possible. So they did this because they wanted to leverage the parallelism in the original transformer encoders. So because of which transformers were very successful was the high level parallelism in the original model. So they tried to preserve that in this vision transformer too. So that was a high level picture of this. So I'd like to go over this once again, how the things are processed here. So simply we break the image down into patches. We feed those patches and we first flatten them. We feed those patches into this layer. This layer projects those flattened vectors to some other space of some different dimensions. Then these layers add the positional embedding to those vectors. They also prepend a CLS token, a similar type of CLS token that we see in the BERT model. Then simply those embeddings are input to the transformer encoder. The output of the encoder, the output of the vision transformer is the representation, is the final representation of the CLS token. This CLS token is just fed into some MLP layer, and the output of that MLP layer is a final representation vector that helps us classify, that helps us classify the input image. So that was the high level review of vision transformers. So now we come to this paper. So what is the work of this paper? What this paper tries to do is it just measures the robustness of VIT models of different sizes that are pre-trained on different data sets and compares the results to the performance of resonance, the previous state of the art. So how do we really test this robustness? There are two ways we can test this. We can either feed the model with perturbed inputs, that is, we disturb the inputs somehow and see if our model is resilient to the disturbed inputs or not. The other way we measure robustness is we just do some other studies like lesion studies. We remove some layers in the model. Mind you, during inference time, not during the training time. During inference time, we remove some of the layers towards the end of the model to see how the model performs without those layers. This is basically done just to see if there is some redundancy in the model. The other way we can do some testing on it is we just restrict the attention span, like we already see in the transformer. I mean, it's all made up of attention layers. We just try to restrict the attention layers to try to see how the model performs if we just manipulate that attention. So that's all in this paper. Major headings for this paper. So let's go on. So as I already said, there are many model variants of VIT. The VIT, the vision transformer model can be categorized based on two things. The first thing is how many trainable parameters are in our model. So there are, on basis on the number of trainable parameters, our model can be divided into three categories: VIT basic, VIT large, and VIT huge. So VIT huge has the largest number of parameters. It has 632 parameters. The VIT large is 307 parameters, and VIT basic has only 86 million parameters. The other way this paper has categorized this VIT is on the basis of the model, that on the basis of the data set that the model has been pre-trained on. So there are three types of data sets. There are three data sets that have been used to pre-train this VIT model. The first of them is the simple ImageNet. It has only 1.3 million images. The second is the ImageNet 21K. It has almost 13 million images. And the largest of them is the JFT 300 million, which has 300 million images. So as we'll see, the model performs the best when it's pre-trained on this ImageNet, on this data set, the JFT 300 million. All right, so let's move on. So let's see the first of those categories of perturbations. When we perturb the input to the model, we just distort the image somehow, but we distort the image in such a way that we as humans do recognize the image, but it is comparatively difficult than the undisturbed image to recognize the image. So the first of them is this natural corruption. So I mean, there's a data set by the name ImageNet C that allows this artificial perturbation of the images. So we can see there are a lot of artificially generated perturbations. For example, this is a picture of a bird, and we have added some Gaussian noise, some short noise. We've added artificially generated snowflakes in this, and a lot of things: contrast, elastic, JPEG, fog, frost, motion blur we can add. There are a lot of things that we can do artificially to, and then we feed those images into the model and see how the model performs. So as we can see, if we pre-train the model on the data set that has a minimum number of images, in this region our resonates perform better than VIT. Mind you, there was no inductive bias in the vision transformer, but there are strong inductive biases in the resonate for computer vision tasks that are already said. There are things like translational invariance in spatial locality that are already inherent to CNNs, and that help it perform a lot better than VIT in the region, in the arena where there's not much data. So we can see in the data set having the least number of images, the resonate performs better than VITs. But as we go on, as we increase the size of our data set, we can see even the inductive bias present in the ResNet, inherent to ResNet, even the inductive bias that is inherent to ResNet does not help it beat the VIT, because there are a lot of connections of because there are a lot of attention heads and attention spans in the transformer. It performs even better than a CNN. So as you can see in this JFT, as we can see on this JFT data set that has 300 million images, the VIT, the vision transformer, huge, and that has patches of 14 by 14 pixels. It performs even better than the high. It performs even better than the best resonant model. So that was the result for these natural corruptions, where we generate those corruptions artificially using this ImageNet C. So this ImageNet C simulates these natural corruptions for us. And mind you, these are the result to this type of perturbation is really very important, because if we deploy our model to some critical systems, we would expect our model to withstand these type of corruptions. So no matter if it's snowing or there's frost or there's fog, you may expect your model to withstand all of those things and perform fairly in all those type of situations. So now comes real world distribution shifts. So these are similar to by this other I don't know, ImageNet R. These type of distribution shifts are simulated by this data set, the ImageNet R, where we see, even though this is a sculpture of a panda and it's not a real panda, we as humans can easily recognize that this is a panda. So we expect our computer vision model to also recognize that this is a panda. So we just test our vision transformer and the resonance on these type of data and see which one performs better. So this type of data is a real distribution shift, real world distribution shift. So this cheetah hair or leopard hair does not look like a real leopard. There are some distribution shifts, but overall the shape, the picture, the shape, the size, the contours are all similar to that of a real leopard and this whale hair. I mean, the overall picture does resemble, but there's a real world distribution shift in this. All right. So yeah. So this is how the two models compare with each other in this. As I already told, in the lower data regime where there's not much data, ResNets perform better than VIT as expected, because there's no strong inductive bias in the VIT. We don't have spatial locality, we don't have translation invariance built into the system, inherent to the system. But as the data increases and as we add more and more images to our data sets, we see the VIT performs at least as well as ResNets, or in some cases even better than ResNets. As you can see here, there's a slight improvement in the performance of the VIT. So as we can see, the data set that we pretend the model on plays a very, very important role, as we can see here. So like on 1.3 million images, they have 20% accuracy, 40% accuracy on 13 million images, and 70% accuracy on a data set having, if pre-trained on a data set having 300 million images. That was for real world distribution shifts simulated by the ImageNet R. Now comes these natural adversarial examples. So as we can see, these are really difficult. These type of data sets are really very difficult for a model to predict. So as we can see here, if we see this dragonfly on this doormat, so 99% of the times, or a model or a ResNet performs, or a ResNet predicts that this is a man who will cover 99 with 99% more confidence than a dragonfly, because we can see the patterns of the doormat and the patterns of a manual cover are pretty much similar. So it's very difficult for the model to predict which is which. And we can see here, if this man is, it looks like he's riding a unicycle, and the model somehow predicts the posture of the man and predicts that he's riding a unicycle, and predicts that it's a unicycle. But we as humans can see that there's a racket in the man's hand. So yeah, so there's more confidence in saying that he's riding a unicycle than there's a racket in the hand, if seen if seen by if seen by a if seen in the eyes of a model, some computer vision model. So these type of data sets are very difficult to predict. Let's see how these models perform on this. Again, the same story, very low accuracy in the image data set, having in the data set having low number of images, and very high accuracy in the regime where there's a lot of images in the data set. So yeah, now this type of study is a very important study. So now we are seeing the robustness versus model size. So how well does the model play if we just scale it? So we see here that if we pre-train the model on the same data set, the JFT 300 million, having 300 million images, and if we scale the model, this is how it performs. The error rate goes down if we scale the model. I mean, this is expected. But the other thing to note here is that the slope of the model, the slope of VIT, the vision transformer, is much better than the slope of the ResNet, which means that if we are successfully able to scale the vision transformer even to bigger sizes, even to much larger number of trainable parameters, we can still improve the error rate. The thing that really matters here in this image is the slope. The slope by which these models improve. That's the thing to be seen here. Okay, now let's come to adversarial perturbations. So these are very advanced type of perturbations. These are also called white box attacks, because these type of attacks can already be carried out if we know the architecture of the model. So these type of attacks, they take into account all the other things that are inside the model weights, the individual layers of the model, how they interconnect, how they behave, how they stack on top of each other. So that's why they are called white box attacks. So mind you, if I prepare a white box attack for a VIT and try that white box attack on a ResNet, it would perform well, and vice versa also. So if I prepare a white box attack for a ResNet and try that attack on, and try the perturbations that I've generated on a VIT, on a vision transformer, it won't work well. So these are the perturbations that have been generated. There are that have been generated through these adversarial attacks. So basically there are two types of adversarial attacks: the FGSM and the PGD. Yeah, FGSM and PGD. So we can see the perturbations. The perturbations are more in the foreground of the image, and we can see a boxy type of pattern when it comes to the vision transformers, because as we know, we break the image into the patches before feeding them onto the vision transformer. So we can see those patchy type of pattern in the foreground of a adversarial attack generated for VITs, and we don't see that patchy type of pattern in the white box attack for the ResNets. But we see one type of a common thing here: the perturbations are more in the foreground than in the background. So now let's come to adversarial spatial perturbations. So what we do in these perturbations is we either shift the image by some pixels towards the right or left, and we also rotate the image at the same time. So we just choose one value among this range, -16 to 16, and we choose one value in this range and perform those translations and rotations at the same time and see how our model performs on this. And these type of perturbations, they are very important, as you can easily get an insight on how the model is performed, how the data is being processed inside the model, as we will soon see. Oh, so this is how the model performs on those adversarial spatial perturbations. We can see the same story here also. The other thing to notice here is that the 32 by 32 VIT does not perform well. The largest of the VIT, where we break down the image into the largest of the chunks, 32 by 32 chunks, 32 by 32 patches, non-overlapping patches. All right, so now let's focus on texture bias. So this is a really important type of a bias that we may want to eliminate in any of computer vision application or a computer vision model. So what we as humans see in an image is we just see the outline of a figure. So for example, if I show you a cheetah and a leopard at night, you just see this outline of the cheetah, and you just figure out that it may be some animal from a cat family. But for a computer vision application, what it does is, for a computer vision model, what they do is they sometimes rely too much on the texture. So for example, there are many types of banana. So some bananas are yellow, some may be green. So if I show a computer vision model a yellow banana, it may well predict that it's a banana. But if I show it a green banana, there is a slight chance that it may not be able to predict it, even though the shape of both the bananas are similar. So just because the texture was different, the model was not able to predict the other type of banana very successfully. Just because the color of the other banana was some other color and not yellow, it was not successful in predicting the other banana. So we simulate a data set for this testing by a technique called neural style transfer, as we'll see in the next slide. So this is neural style transfer, as a lot of you may know. We just give it an image and a pattern, and we just somehow fit the texture on the image. Outline of one image and the texture of the other image. That's what is neural style transfer. So how these two models perform on this type of data set, on this neural style transfer data set, is we see that larger patch sizes in VIT seem to perform very better. They somehow seem to preserve the shape better than the VIT that uses smaller patches. It's very contrary to what you have seen before. Before we have seen that a VIT breaking the image into smaller patches perform well in all of the tasks, in all of the input perturbations we had seen earlier. But now what we see is that a VIT that breaks down the image into larger patches performs well. So this is very strange. One reason we can give for this is that larger patch sizes may preserve the image shapes better than a VIT that breaks down the image into smaller patches. We also need to see here that the resonant performs much better than CNNs in this regime when there's a lot of data, when we pretend them on the JFT. All right, Now comes model perturbations. Before, what we did is we just did some perturbations with the input to the model. Now what we're doing is we are just playing with the model itself, the architecture of the model itself. Maybe we may cut down some layers, we may cut down some um, what do you call them, you cut down some layers of the transform model, the transform encoder, the self-attention blocks, what we call them. We may cut down some uh, layers and see how that performs. What we also can do is we just restrict attention of the layers and see how it performs. The other thing that is really very important here is the layer correlation. So as we will see, there is a lot of redundancy in the vision transformer. So we can really prune out some layers during inference time, and the accuracy won't go down too much. All right. So the first of them is this layer correlations. As you can see in the image. So let me just give you a brief idea of what these images do. So we just are measuring the correlations between the representations of each layer. So as we know, this transformer encoder is basically a stacked layer of blocks, where each block is a self-attention layer. So what we do here is we just measure the correlation in the output of each of those layers. So as we can see, there's a lot of correlation in the output of those layers towards the end, as you can see in this image too. So lots of correlation between the outputs of the layers. Lots of correlation means lots of redundancy. So there's a lot of similarity in the outputs of each of those models towards the end. So does that mean these layers are not necessary towards the end? What I'm trying to ask is, does that mean that layers towards the end are not necessary, since the correlation in the output of those layers is quite similar? We'll see how it goes. So this is the CLS token correlation. Remember CLS token, token that went to the input of the embedding layers. This is its correlation. So what we see is that its correlation is very high towards the start of the encoder, the start of the model. That is in the that are towards the start of the model. It does not change. I think my connection is lost. Hello, am I audible?
Yes, you are.
Oh. So what I was saying is, we can see from those images that the CLS token does not change much towards the start of the model, and it starts to change quite drastically towards the end layers. So what this means is that the model does not pay much attention to process the CLS token towards the start. It only starts to process the CLS token towards the end layers. What's said here, CLS token, the token prepended to the sequence of patches, and its representation changes very slowly towards the start, but changes very rapidly towards the end. So what this hints is that the later layers are devoted more towards consolidating the CLS classification tasks than bringing the change in the representation vectors. As we saw, the representation vectors were very slow to change throughout the layers, especially towards the end layers. As you can see here also, you can see there's a lot of correlation of the representation vectors towards the end. So it means it changes very slowly. And it's quite opposite for the CLS token. The CLS token changes very slowly towards the start of the model, and it changes quite rapidly towards the end of the model. So what we make out from it is that the CLS token is processed towards the end layers, and it's vice versa for the other representation vectors, for the other embeddings. So now we do the lesion study. That is, we prune our model. Uh, we prune our model during the inference time, mind you, not during the training time. So what the previous results, the correlation results, uh, force us to ask is that, because there's a lot of correlation and a lot of redundancy in the model itself, so is it wise to keep all the layers during the inference time? I mean, do they play any real meaningful task during inference? So what lesion studies show is that we can remove layers from already trained networks during inference time without much degrade in the performance. But as we remove more and more layers, the result does go down. But if we do just a single layer in the model during inference time, the result does not drop much. The other thing that's quite shocking is that larger models are more robust to layer removal. Sorry, the thing that is shocking here is that the models that are pre-trained on larger data sets are less robust to layer removal. So if I train a model on some very large data sets and I remove a layer, the drop in performance will be much drastic than if I train the same model on a data set that is not as large. So what this tells us is that there's a higher utilization in models trained with larger data sets. So a model trained with larger data set utilizes each of the layers much properly than a model that has not been trained on a data set as large. And removing individual layers hurt less than removing the whole encoder block. So as we know, a self-attention block consists of a self-attention layer, and there's an MLP, and there's a skip connection in between. So if we remove the whole block, the drop in performance is much drastic than if we remove a single layer. For instance, if we remove the self-attention layer only or the MLP layer only. So these are the results for this lesion studies. We can see when the model is trained on a huge data set and we prune the model during inference time, the results are quite shaky than the results of a model that are not trained on such a large data set, as you can see in the image. The upper row is the result for removing a single layer. The lower row are the results for removing more than one layers. We can see if we remove just a single layer, the results don't vary much and it's not much of a drastic change. But if we remove more than one layers in the model, we can see the performance drops quite a lot. So now comes restricted attention. So what happens if we restrict the attention during the inference time? So how we do this restriction is that we use a certain distance based mask during inference. So the authors don't talk about it in much detail in the paper, but it is some spatial mask that they use to restrict attention. So what they see is that restricting attention in the earlier layers hits hard. It hits hard, but not much in the later layers. If you restrict attention in the later layers, because a lot of processing has already been done in the earlier layers. So even if you restrict attention in the later layers, it won't affect the performance much. As we already saw in the correlation studies, is that the representation vectors don't change much towards the end of the layer towards the end of the model. It's only the CLS token that is changed towards the later layers. So that's what is reinforced in this study also. So this is how the model performs as we go on restricting attention. As we restrict attention to less and less number of distances from the representation vector, we see a strong drop in the performance. There's one more thing to notice here, which I forgot to tell you, is that we cannot restrict the attention of the CLS token itself. CLS token is allowed to have self-attention calculations with any of the other representation vectors. We restrict only the self-attention for the other embedding vectors, not the CLS token itself, because it's the CLS token representation vector in the end layer that we use for a classification task. We cannot restrict the attention of the CLS token itself. That would mean that there's no computation going on in the model. So yeah, that's it. Thanks a lot. Yeah, I can have questions now if there are any.
Okay, so any questions?
I have a question regarding the attacks he mentioned in the paper. Can you tell something about like FGSM and PGD attacks? Like why I didn't understand that particular part. Why in PGD this thing is better and FGSM that is better, and what is like the major difference between the both?
I mean, it's some very high level attack that they do not talk about in the paper, but they just tell that it's a white box type of attack where you keep the model type into the consideration, and each of the model layers and their interconnections and how they play in the model into consideration. The authors don't talk about it in much detail in the paper. They just say that there's a drastic decrease in the performance of the models when you perform such attacks.
Okay, thank you.
I have a question. Could you go back to the slides talking about the ResNet? I mean, at the very beginning.
Yeah. Yeah.
Yeah. I'll go to the one slide more. Yeah, this slide. So, sorry.
The other one?
I mean,
should I go left or right?
The later one. I mean, so it's a figure. Yeah, this one. Yeah, this one. So the residue connections, you mean like they can allow easy gradient flow to the early layers and prevent the gradient vanishing. So what did these conclusions come from? Like what paper are you referring to for this kind of stuff?
I mean, there are a lot of people that are mentioned in the that are mentioned in the paper itself that talk about this, that give a reference of it. I mean, like it's.
Oh, I mean, for this page, like these conclusions are from which paper?
This conclusion from Facebook. I mean, I don't remember.
Are they from the ResNet paper or?
Yeah. I mean, they are from the Resin paper also, because in
but from my understanding, when I read the Resin paper, they are talking about that the gradient vanishing or exploding gradient has already been addressed by the batch normalization, and the ResNet, the residual connection, their design is not to solve these issues.
I don't know, because I saw a lot of papers that talk about this, because there's an easy flow of gradient towards the earlier layers that escapes much of the functions, because a skip connection is just it allows us an easy outflow of gradient, and it just restricts all those calculations in the processing in between. That's why, I mean, like as you can see in RNNs also, there's a lot of gradient vanishing because the gradient has to flow throughout the layers in between.
Yeah, I know that, but I mean the vanishing or the exploding, these two issues, I mean, has already been addressed by the batch normalization, and this claimant is directly from the resonance paper.
I don't know. I'll have to look into that.
If you read the paper, it is very clear in the introduction, and then they mention another scenario about the deep learning that they found that the performance degradation is because sometimes it can be very hard to optimize. And also they found that the performance degradation is not caused by the overfitting. And then they are trying to to do the, then they bring up the ResNet. But in their paper, at least for the ResNet, they are not claiming they want to use ResNet to prevent the gradient vanishing or exploding gradient. So like, I mean, you can add a citation about where this conclusion coming from.
Oh, all right. So I don't remember, because I saw it somewhere in the paper or some other paper that I saw. I forgot to add it into the references. I'm sorry for that.
Oh, it's okay. Thank you.
Yeah, so any more questions from the students?
I have a question about the redundancy, actually. So, I mean, they find out that like there's a huge redundancy, especially when you go to slide 36, I guess, with the matrices or 9. Yeah, with the matrices, like in this, for example, in this slide, we see that there's a lot like redundancy. So, do you think that I mean, if there's a lot redundancy, so the model has can already do it with less layers, they say that in inference time they can reduce maybe this redundancy, but can we not include decrease this redundancy in the training time maybe? Also, it basically means that a smaller model can also just has encode this information that a bigger model encodes, because it has a lot of redundancy. Do you think is there a way to make it more efficient?
So what I think, they are not trying to reduce the redundancy. They're just making use of the fact that since there is a lot of redundancy in the model itself, they can skip some layers, and it's not possible in the inference time, as they say, because during inference time, it has been seen that if we decrease the number of layers, the performance does decrease. So it's not like the smaller models are as robust as the larger models. There is some task that larger models do play quite better than the smaller models. So even though there's a lot of redundancy in the layers itself, larger models do perform well than the smaller models. It's just the fact that they can remove a certain layer, and that there is not a lot of drastic change in the accuracy and the accuracy of the model, as I already show in this slide. If you just prune out one single layer during inference time and not during the training time, there's not much degradation in the performance, even though there is still some degradation in the performance. But as you keep on removing more than one layer from the model, even though there is some redundancy in the model, even though there's some redundancy in the layers itself, the output does go down. So what the authors have not talked about this dilemma here. And what they're talking is, there is redundancy in the model. There is a strong correlation between the layers. We can see there's a lot of correlation in the layers, but even then, when we prune out some layers during the inference time, the result does go down. So this is still unaccounted for. There is a lot of correlation, but we do not know why the output still goes down when we prune out the layers.
Yeah, maybe just the model has to be trained in a way to prevent this redundancy. Maybe during training time, we can find some auxiliary loss that would try to make all the neurons, so to say, not correlated to each other, that, and loss that punishes the correlations between the image, between the
yeah, exactly,
between the neurons, that would maybe and just like enable us to train a smaller network than with less redundancy. But I guess that this architecture, like redundancy, is not avoidable.
There's one more reason I can think here is that since we are waiting for the CLS tokens representation to evolve, as you can see in this figure, towards the start, the CLS tokens don't change much, but it's towards the end that CLS tokens change, because as you can see, there's no correlation towards the end for the CLS tokens. So maybe this model is waiting for the representations to develop to the highest level and then start working on the CLS tokens and then start working on the representation of the CLS token. Maybe this is the reason, working for the CLS token towards the end and not working for the representations at that time when you're working on the CLS representations. Maybe that's the reason. Did I make my point through? Did you understand what I said? Working on the CLS tokens towards the end and working on the representations towards the start layers. We are just looking at one picture of this here. We're just looking at this representation. We are just looking at the representation of the embedding vectors here and not CLS tokens at the same time. We have to look that there is some work going on. In the start, the representation vectors are getting developed. Towards the end, the CLS vectors are getting developed. The model is not sitting idle in any of the layers. It's just that it's working on different part of the problem.
Yeah, I see. But like what I was only trying to understand if there's a way to just like still, even though like the model works on something in the later blocks, still like there's a lot of redundancy, like all these like other tokens, all other tokens other than the CLS token are being trained, we calculate derivatives, we do backpropagation, but we're not gaining almost anything from that. Like, so like if, yeah, there's probably, that's a huge study where like someone can like work on it to optimize that, like in the later, like in the later layers, we can maybe just like reduce the redundancy in all the other tokens other than the CLS token, because like even though there is a high correlation, it costs us the same in terms of computations as the CLS tokens.
Yeah, I get it. Some part of it I got, yeah. Yeah, I think there can be an auxiliary loss, as you already said. And maybe by introducing that auxiliary loss, who knows, the model performs even better. When we just force the model to learn something new in each representation and not just present the same representation of the other layers, maybe, who knows, the model performs even better when we discourage such correlations.
Thank you.
Yeah.
Okay, so any more questions? If we have no questions, then probably that's it for today. And the paper is it's more like an experimental paper, right? So we have so many experiments results. I mean, we also draw many conclusions based on observations in this paper, and they try to analyze this VIT model in more detail, right? With a focus on the robustness of the model performance. Okay, so the paper is very interesting, right? And the talk is also good. So, and this second speaker. Also a reminder for you, I mean, so the proposal will be due by this Friday. So I think it's time for you to work with your teammates to submit the proposal to the Canvas system. Again, I mean, only one copy will be needed from one team. So you can elect one team leader, then ask the leader to submit the report or proposal to the Canvas system. Yeah, if you have any question for the proposal or you have any unclear process, you can let me know. We can either talk about, at the end of the class, or you can also send me emails. Yeah. Okay, let's thank the speaker. Thank you so much for the talk.
Thank you so much.
Can we maybe just like, so we like landed on a basic idea, but we couldn't like have time to, because it was a little late, we couldn't have time to discuss, like maybe just like get your opinion about our proposal idea. If you can, I just like introduce it in like in 2 minutes and then try to see what you think about it.
So for the proposal, it's not planning for your paper, right? So the main issue is because this quarter is very short. And my suggestion would be you can think only, right? And you can have only planning for your paper. Then for the proposal, my suggestion, you need to think about the problem you plan to study, the technique and the model you plan to propose. And if you can provide more detailed information for the model, you can write down into your proposal and also include the experiments you plan to do, all the data sets, the training process, and so forth. Right? It's more like a detailed planning for the paper. Right? And so, yes, my suggestion is you can start early, right? So you can think early. You don't need to wait until the very end of this quarter to plan your paper, right? And you can think right now. And it's not this proposal is more something like a data line to push you to think about your paper, right, and the project. So you can utilize this opportunity to push yourself and your teammates to start work on the project right now and to think about detailed things.
Okay, and are we gonna get like any feedback on the proposal to just like, I mean, if it's a good idea or not after submitting the proposal?
I cannot
Just
hear
like-
you clearly. Can you say again?
So are we gonna get a feedback about the proposal after submitting it, or is it just like, I mean, we are gonna start working on it?
Sure. So if we find any drawbacks or some serious problems from your proposal, then we will provide with some feedbacks. If everything is good, then you can just, I mean, we also let you know if everything is good, then you can just do as your plan in the proposal. We provide with some feedbacks.
All right, thanks.
Yeah. Yeah, any more questions? If we have no questions, then probably that's it for today's class.
Hi, Professor Zhang. I just sent you an email about some students just asking about our grading policy about our final project and the proposal. So maybe we should get an announcement. So maybe just 3 or 4 students just ask me these days. So maybe we should send a announcement about how we grade our final project and the proposal.
Okay, I will send an email to everyone. Yeah, sure.
Okay, thanks.
Okay. Yeah, Manisha, do you have any questions?
Hi, Professor. I have a question regarding the proposal template. I see like in the Canvas, you have updated a link on the proposal template. So I just wanted to confirm whether it is the whether it is the interim sample PDF under that website. Is that the template that we are supposed to follow?
No, in the downloaded template, we have so many different templates, right? You can click into one folder and you can find one template. It's called SIG conference, right? Or SIGconf. And we would mention the template name in the slides, also in the syllabus, right? You can check the specific template we plan to use for the proposal. It's called SIGconf, right? It's SIG conference, yeah.
Okay, Professor. Like I just click on to the link, but
you can link.
Yeah, in the syllabus page, there was one link that says like maybe can I share my screen, Professor?
You have access to the syllabus, right?
As Professor. So I was just talking about this one. So there's one link for the proposal.
The next one, the next 9.
Okay. Okay, Professor. Thank you.
So you can download it, right?
Okay, Professor. Thank you.
Yeah, no problem.
Bye.